Hello, and a very warm welcome to the web seminar on drone-based NavAids inspection from Colibrex and FCS Flight Calibration Services, hosted by LS Telcom. My name is Luc Heberle, Managing Director of Colibrex. And before going into the details of our topic from today, let me give you a short introduction on who we are and on our presenters. Colibrex is a subsidiary of LS Telcom, worldwide leader in spectrum management and spectrum monitoring solutions. At Colibrex, we are specialized in drone for radio frequency measurement. We have been pioneer in integrating RF receivers in modern drone technology. We have started a few years ago with broadcast antenna measurement as example, and meanwhile we have extended the application towards spectrum monitoring. A typical use case here is interference hunting. Actually, every time when it comes to picking up an RF signal in the air, there is an interest to do it with the drone. And these can also apply for the NavAids inspection. And when we decided to enter this field, we started a cooperation with FCS Flight Calibration Services. You may know that FCS is a joint venture of three major air service navigation providers of Europe. The DFS, Deutsche Flugsicherung from Germany, Ostrocontrol from Austria, and Skyguide from Switzerland. So having FCS as a partner for us is of course a very good help because we can benefit from their expertise in this CNS field. And we are very glad today to have Dr. Joren Bredemeyer as one of our speakers. Joren has heavily contributed to the development of the NavAidDrone and especially to the development of the special receiver that we have integrated into this solution. This technology highlight is actually also the result of many research projects, most of them made with the PTB. PTB in Germany is the National Meteorology Institute and actually the highest authority when it comes to accurate and traceable measurements. So having them as a partner, backing up our technological approach is also a very good asset for us. Joren will, in his presentation, this will be the second part of the web seminar, will give you some explanation about the technological challenges that we had to manage during the development of this NavAidDrone, the NavAidDrone, by the way, that you see here on my right. I will start then with a first session, a first part, dealing with the targets and the drivers actually of using drone in the CNS field. And the third part of this web seminar will be conducted by my colleague Cedric Gonzalez. And Cedric will make for you a live demonstration of the software that we are using in the NavAidDrone, because we decided actually to put a lot of attention, a lot of efforts in developing a comprehensive software to deal with the complete workflow actually of drone measurement for NavAids inspection. So I guess this will be for you a very interesting part. We do hope that the Teams system will work fine this afternoon. We had some issue we had a first session this morning. We had some issue with the connectivity with many attendees, but hopefully we found a way to manage that in a good way for this afternoon. Before starting the presentation, let me allow me to make a last comment in this introduction. In the current situation, where the aviation industry faces a critical crisis, we believe that efficiency in all the procedures that apply to flight safety are probably more crucial than ever. And our target, our ambition is to provide a certain contribution with the NavAidDrone. That's probably also the reason why there are such a high interest into this web seminar. For your information, we have counted more than 120 registration over the two sessions, representing over 100 organizations from 53 countries. So the web seminar will last approximately 1 hour, including a Q&A session. If you have some question, you can write them in the chat window, and we will try to answer them at the end of this web seminar. The web seminar will be also recorded and made available for you in case you want to replay it. All right, then it's time to start. I will start with the first session, and while I will move to my presentation screen, we will just show you now a very short video with some impressions of flight, of measurement that we have recently did with the NavAidDrone. So you see a few pictures of our operation in various airports. And here, a short video overview of a start at the middle marker for glide path measurement. We will go a little bit more into details on that later. You see here the flying going up, typically 150-meter high. And here also, to finish this small introduction, an overview of the drone flying during night. This is, of course, one possibility that we have. I will now switch over to my screen and start the presentation. So the title of our web seminar is, as you know, the benefits of NavAidDrone. I have already mentioned actually the three sessions that we intend to conduct now, the three parts of the web seminar. You see also a picture of all three presenters that we have for this afternoon session. Let me start with some introductory word about what we consider the drivers for the use of drone in CNS inspection. We believe that ELS will remain a key element of instrument approach procedures for many years, even if there are some new technologies, some new systems like GNSS-based solution, but especially for Cat3 because of the solid, the proven, and the independent way how the ILS system are operated. We still think that they will be used for probably many decades still. On the other hand, we know that the maintenance of the ILS system can be quite demanding and expensive, and that you are looking for some solution to optimize that. And this is where we want the NavAidDrone to be a good, to offer a good contribution. And actually, we have two main targets. The first one is an improvement, including cost saving of ground measurement procedures. So here we see the NavAidDrone as an alternative to existing technology, to existing system. And of course, we see also as a target the saving of inspection hours in some specific situation for some specific task. We will come to that a bit later, also with the important topic of the extension of inspection period with the flight inspection. At the end, we will also show you a little bit what else we intend to do with the drone in the field of CNS in order to leverage the usage of drone in that field. Then I immediately continue with a very, very typical application where we really see a huge benefit using the drone compared to conventional methodology. The conventional methodology to measure a glide path is the use of a telescopic mast in most of the cases, with a lot of limitation. You have, because of the limited height of the telescopic mast, you can only position it near to the antenna. That means in the near field, the signal in space is not yet formed. We have a limited height, a limited angle of measurement that we can cover. And also an important topic, the runway must be closed when you install telescopic masts on it. Whereas with the drone, we can, for example, go a bit more far away, typically 1 to 1.5 kilometers from the threshold. This would be at the middle marker. And here we get a representative glide path signal over the full vertical coverage, which is obviously not possible with a telescopic mast. The other, and the NavAidDrone can then fly the complete reference angle that is necessary actually. So in addition also to a better measurement capability that we have with the NavAidDrone, we see a lot of operational benefits. The NavAidDrone can be deployed in a very short time. This is then even possible during the day. No runway closure is necessary. Yeah. Also, in case of emergency, an escape can be made very quickly. I will take this opportunity to show you a small video. I hope that this will work fine this afternoon. Here, actually, what we want to show you is an example where the drone is in place at this level of approx 1.5 from the kilometer from the threshold, or even less in that case, where you have an aircraft which will land. We are ready to take off with the drone. And actually, we are now just waiting for the clearance from the tower, and we can start the measurement. So we believe this is a very, very important aspect to be considered in terms of operational gain. Now you should see my screen again. Here, as I said, you see on a large airport 4 takeoff points that we had in order to measure the 2 ILS, the 2 glide path system from each runway. In this case of a big airport, these takeoff points are within the fence of the airport. For some smaller airports, of course, this can be outside. That depends really on each location. Typically, how do we proceed? You see here a kind of representation of a flight sequence. If we have, for example, clearance for 15 minutes from the tower, then we can launch the drone and in the mission, plan it for several measurement sequences. In this example that you see on the screen, the drone goes up, measure the transmitter 1, then we can let the drone wait a little bit in the air. During this time, the ILS technician can do the switch of the transmitter. It goes down, measure the other transmitter, and we can repeat that, for example, with the alarms, with the different alarms condition. Yeah. Then we land, then we do the post-processing of all the data and check the result. In case you don't have such a large window of operation, what we can do is simply use a 5-minute slot and launch the drone for vertical flight, up and down, do the measurement, do the post-processing check, and then we wait for clearance for the next operation. So this is actually very easy as soon as you have got a good communication with the corresponding tower. All right, some other application that we can do typically with the NavAidDrone when we are talking about replacement of ground measurement techniques would be, for example, the measurement of a localizer, especially the displacement sensitivity, clearance and width factor that we can here measure with so-called arc flight, so orbit flights that where we can well cover the coverage area. Some of you have already asked us in some previous communication about the possibility to use an NavAidDrone for the runway course. Here we have to admit it depends very much on the type of flight authorization that you get from your authority. Yeah? Because typically we fly at a line of sight, and in line of sight we are limited to, let's say, plus minus 500 meters. To cover a complete runway, this might not be enough. So either you get an authorization to fly beyond line of sight, the drone can do it, of course. Question also of tracking of the drone, of UTM technology, and so on. These are a bit topic for the near future. But we can also consider to do the measurement in different sequences. As an alternative, we have also decided to offer a special setup that we call the NavAidDrone receiver car integration. The idea here is to use actually the same receiver that we have, which is in a housing that you can detach from the NavAidDrone and put in a special arrangement in a car with an external antenna and an external GPS receiver. In that case, you can use the equipment also for the runway course alignment, and you don't need to acquire a separate receiver. So now let me come to the very important topic also that you have, because we receive a lot of questions on that issue, is in which extent is the NavAidDrone, can the NavAidDrone help to reduce and to optimize flight inspection? Maybe I forgot to say before that definitively the NavAidDrone is not a one-to-one replacement of a flight inspection aircraft, simply because with the NavAidDrone we cannot fly the same coverage area. The flight inspection is of course subject to an extremely high certification process. This is something which is not dedicated to the NavAidDrone, but in some specific situation, an important situation actually, we can use the NavAidDrone to do similar type of measurements. Like you see on the slide, glide path or localizer axis, width, clearance, the alarms of course, and the phasing, an important factor. And this can be used for adjustment work, as continuous reference measurement, for example, for preventive maintenance, very important topic, and as pre-check before the flight inspection. The idea here is to do the commissioning of a system with a NavAidDrone, and then you ask the flight inspection aircraft to come only for the final validation in a certain way. And in such a way, you can spend several hours of flight inspection. And then here you see, an example of the NavAidDrone flying what we call an engineering approach, typically in the 3-degree glide path angle. Yeah? And you see on the right, actually the flight plan is very similar to a section of a flight inspection sequence. Yeah. And then to conclude this part on optimization and reduction of flight inspection, there is this very important topic of how in which way can the NavAidDrone contribute to the extension of flight inspection intervals. Most of you probably know what ICAO is saying on that subject, that a prerequisite for the extension of flight inspection intervals is the availability of reproducible and accurate ground measurement data, and that you have to do a comprehensive work of correlation with these results. And this can be achieved when performing regular and continuous measurement with the NavAidDrone. You need, for sure, a high sample quantity in order to achieve a very well-founded statistical observation, but this is the target that we have with the NavAidDrone. We have to say we see the NavAidDrone here in that sense as a tool that you may use in order to do this correlation work. But the correlation work, the correlation concept, must be established and authorized by each local authority. This is what ICAO and what the government mentioned. All right. With that, I have finished the first session, and I will slowly hand over to Joran, Dr. Joran Bredemeyer from FCS, who will explain you a bit more in details the challenges that we face with such drone-based ILS measurement. As you can see on this first slide, we consider that to get a versatile, accurate, safe, and also easy to operate ILS measurement drone, we need all these challenges to be really well mastered. And here we have to cover topics like the receiver technology, the measuring antennas, the position accuracy, the position integrity, very important factor, and also some drone safety features and drone operational conditions, which are maybe not so much the topic for today, but that we need to mention. And what we really want to underline is the fact that, just in our opinion, just putting any kind of ILS receiver on a drone and having the drone flying and maybe doing some measurement is one thing, but having a complete, a comprehensive and accurate system taking into account all the factors that I have just mentioned, this is another challenge. And this is the point where I would like now Joran Bredermeier to give you a bit more explanation.
Hey, Luc, thank you for that introduction. Good morning or good afternoon, everyone from my side. I'm gonna tell you a few things about the receiver and some other topics, which include altogether 4 slides. Well, generally, I'm not a friend of lab receivers that are mounted on drones. Luc already said a few sentences about that. We prefer using dedicated receivers that we developed on our own for this special use case. And regarding this concept, the receiver and the signal processing is built on a series of forerunners on the so-called SISMOS, which means Signal in Space Monitoring System, that we developed at FCS, and that was formerly mainly in use for analyzing multipath propagation effects, because we can look into many details of. One example is given here on the slide. I will put the focus later on that. Well, the receiving and signal processing concept consists of a variety of RF front ends and for all the necessary frequency bands, including ILS and some others as well. And on the hardware side, we have an FPGA-based digitizer board and an SSD where the data are stored in a raw format at a very high bandwidth. One very beneficial item is that we have a clock distribution that is fully coherent with a very stable oven-controlled oscillator reference, so we are able to determine some parameters like frequencies and other things that deal with frequencies very accurate. And well, the SDR process for analyzing the signals is adapted to the signal in space itself. So we have implemented some nice correlation algorithms either to mitigate multipath propagation, and also the self-induced propeller AM that we have on drones when they are rotating blades. And there's one example given on right bottom. You see the frequency spectrum, in this case of an ILS glide path. You see in the middle, the center of the carrier, and then you can monitor the 2 sidebands, upper and lower sidebands on 90 Hertz and 150 Hertz, and you see many more spectral lines, and these are induced by the propeller modulation. And well, if you want a very clean and stable DDM curve out of this, we have to cancel out most of the stuff here, and well, this is done with some special algorithms I implemented there. One or the many other beneficial things are included, like the controller, like the firmware of the device that is directly talking to the flight controller. This it's very important because we load up a mission plan, and which we need then to work on during the flight time, and we have to respond to all the real-time mission items that come from the flight controller to start and stop some actions that are necessary. Well, all in all, it's a very compact design of extremely low weight and power consumption. Because it is adapted to the use case and also to the type of drone, to the model that you saw next to Luc in the beginning of the session. Well, another very important part of measuring signals in space is the right antenna. and it's not too easy to choose the right antenna for this task. And again, I'm using here dedicated antennas that we simulated before manufacturing to see if it's worth using those types of antenna. And then on the right top, you see the bow tie antennas for the VHF, and you can hardly see the short Yagi for the UHF. But these antenna types are optimized for the drone itself, because the drone as a whole, the entire drone, is the antenna and not only the radiating elements. So the three-dimensional radiation pattern is heavily impacted from the corpus of the drone, and you have to consider this all in all, and you need to make a very accurate full-wave electromagnetic simulation then for you to decide if this antenna might be appropriate. So we did that, and due to strong connection to the German Metrology Institute, the PTB, we can also make kind of validation, because we can put the complete drone in an anechoic chamber, or even in a smaller antenna scanner, and to see, well, what is the real life three-dimensional antenna pattern, which can also be tested on an open area test site. And another ongoing process is even to measure the absolute field strength very accurately. So if you try to do that, you have kind of traceable field strength measurements, and this is something not too easy to realize, because you need to know your absolute antenna factor in the three-dimensional case. And this is still an ongoing project, and well, we made some nice progress on that, but we are still working with that. This is not an item which is very clear to ICAO, or which is a strong need for all of the NavAids, but we saw in Germany that, at least for the ILS localizer part, the absolute field strength is something very critical. Well, the antennas, all in all, form an optimized system, easily to mount and to remove. It has some integrated connectors, and well, that eases the pain to assemble and disassemble the whole octocopter when you are short on time before starting up the measurement process. Well, one other interesting part is to measure the correct position. While we are using a very accurate high-end RTK GNSS system that has the possibility to use either online or base rover corrections. And for that, you need a very powerful real-time data link, and you need to interface and to manage all the real-time demands. And of course, you have a variety of latency times, because the GNSS receiver has a latency time, and the SDR processing has as well a latency times which are not identical. And you know, in a moving system, you have to compensate for those influences, and that has been done very carefully in a large series of tests that we carried out for that. So all that is included in the processing, and also very important is, of course, the coordinate transformation process, which is done in the system software afterwards. And that requires, of course, a very accurate facility database, including all the coordinates and various types of geodetic data, since we have to transform the WGS84 coordinates into ILS local coordinates for the airport. And another important issue is that you need, for a moving system, a very high position update rate, and the RTK system we apply is able to use that, or to deliver that up to 100 Hertz. And the so far measured horizontal accuracy and vertical accuracy is within centimeter levels, as you can see in the short table on the top right. Some words on receiver accuracy and calibration. So what does ICAO require? Well, we have the Bible, the so-called Bible for flight inspection, which is the ICAO Doc 8071, and well, the doc mentions ILS signal and space tolerances and the necessary uncertainty of the equipment, and among that also the allowed uncertainty of the receiver. We can if put together, we can conclude that the measurement equipment must be 5 times better than the facility. That means, for instance, for the ILS localizer Cat3 core structure measurements, that you need to have an equipment which is better than 1 microamps, which equals to 0.1% DDM. But apart from the Doc 8071, there's another general document that concerns measurements as a whole and uncertainties in general. This is the so-called GUM. GUM is the guide to the expression of the uncertainty in measurements. Well, the document is not addressed really by ICAO, because ICAO does not concern an overall end-to-end calibration, including all states, like the case that we are operating in a dynamic state. Well, as I said before, this is not covered by ICAO, but in our system, this is an ongoing process for NavAidDrone to obtain a calibration which is GUM conformal. Well, now back to the receiver. Well, normally we calibrate the receiver only on ground in the lab. This is the general procedure for calibrating flight inspection equipment. This is done in the lab with very clean and stationary signals, which is the worldwide standard for that, and ICAO recommends that. And since we are a flight inspection company doing regular ICAO flight inspection, we currently apply the same standards of calibration that we have for our aircraft. We apply that also to the drone, and that means currently that we calibrate our NavAidDrone on the same intervals of 30 days, which in Germany the regulator requires. So this short interval is a requirement in Germany, not worldwide, and it does definitely not mean that the short calibration is really needed for the receiver, which is a very stable device. But since we carried out many calibrations so far, we came to the conclusion that we are very well within the given ICAO uncertainties. And so we operate now 3 receivers, and all of them undergo this calibration interval and get a calibration certificate afterwards. And well, it looks like that we are very well within the ICAO uncertainties. Yeah, thank you. That's all from my side, and I will hand over back again to Luc.
Thank you very much, Joran, for this very impressive explanation about the technology which is behind the NavAidDrone and all these challenges that we have mastered. And now I would like immediately to hand over to Cedric, who will show you a bit more on the operational way how to use the NavAidDrone, thanks to an explanation about the structure and the software.
Thank you, Luc. Thank you, Joran. Also very warm welcome from my side to everybody. Start with only with one slide. I thought it was I think it's quite important to understand maybe to have a general overview of the system, because when we speak about the software side, we often see only the visible part of the iceberg, let's say, the one that we can see for mission planning. But Joran mentioned the radio link, importance of the radio links. So if you look on the left part of the screen, so the drone part, we have the autopilot, the flight controller, we have the NavAid receiver, and then in between we have our companion microcontroller. So we have software everywhere in all those components, which we need to make them communicate all together. And then all this part then is also linked using the radio link to our ground station software, so the NavAids software. So all the communication is going through this radio link, and as well as telemetry and also live data during the measurement. Now let's start with a demo of the software. Okay, so this is our we call it NavAidDrone client software. So actually, Johan mentioned during his presentation the importance of the database, and I realized this morning when driving to the office that I started my career 20 years ago now, and I've always been working in the software industry. And also for those of you who knows already LS Telcom, database is a key element of any software. And obviously this is also a key element of our software, the database. Database consistency, database accuracy is a very important part of the software. So obviously, then you will find in our database all information regarding airport, information regarding then a runway, from each runway to different ILS information, the localizer, the glide paths. We have some safety features that you cannot change data unless if you click some edit point or edit checkbox. Then we have some additional important information, important point list, because in all our software we also use a lot of dedicated coordinates. For instance, for the base station, for the RTK base station, so we most of the time use a already surveyed point to position our RTK base station. An important feature here is that we can save, for instance, also picture in the database. It is important because if you go every 6 months to an airport and 6 months after you don't remember exactly where is this point on the ground, and having the picture in the database can be really useful. So to find a small dot where you have very accurate information, position information. So this is, we have then the database. Then as in any software, you have advanced parameters or settings of the software. So in these advanced parameters, we have different type of settings, some safety settings, such as the geofence margin. So the software automatically generate geofence around the flight path. We have some safety regarding the maximum speed, regarding the maximum distance from home, so to avoid any mistake from the operator that could program a mission which is not at a reasonable distance from the home location. It should be even less than that. And then we have also some settings for the measurement itself, like some offset for the antennas, etc. Once the database and the advanced parameters are now well configured, the typical first step is to set the RTK database, the RTK station. As we say, everything needs to be very accurate. So one part that can be done, or what has to be done on site, is to set up the RTK position. So the RTK setup will open window where you can select airport and runway and then select your point from the database, or alternatively you can select N-trip network to make this online correction. So far we typically prefer to use the local base stations, otherwise you rely always on mobile network, and we never know what can happen during the flight with mobile network. Then I cannot do it now because obviously you need to be outside to get those information. So that's why I do not connect to the drone. After that, I will just show you short videos of setting up the system outside, and also of the real flight and what we could visualize from the ground station. So then we can select our airport, select our runway. That's the first part of the mission, preparation of the mission. We select the RX options, so the receiver options. So we have localizer, glide paths, and VOR capabilities. Then for each RX selected, we have different measurement definition. And for each measurement definition, we have then dedicated presets of parameters for the flight calculation and different parameters available. So for instance, if I select for glide path, so we have for glide path this vertical slice that Luc mentioned during his presentation. We have the engineering approach, then using different references, glide path or threshold as the origin. And then we can also perform some engineering sector arc. So we have defined engineering, meaning that we are almost free of any kind of flight for very specific measurement analysis. So a typical flight for glide path would be then the engineering approach and the clearance and vertical slice. Then once you have selected your measurement definition, then you can define, you can select a specific point from the database or select a distance from the threshold. So using the threshold coordinate system. So typically we can also use a point which is marked on the ground. So yeah, then we can also, then it means that all measurement will be then performed at this location for the vertical. Automatically, we have the distance to the threshold, the distance to the glide path, and then based on those distance, then the automatic start and stop height are calculated. So we use as a parameter the theta, which is this multiplier of the glide path angle. Again, everything is related to database. So typically, in that case, our glide path angle in the database should be 3 degrees. So then it means that we are measuring or we want the measurement from 0.9 to 6 degrees. Then we can set different glide path conditions. So which is, it doesn't have any direct influence on our measurement itself, because these are the alarm conditions, you know, which are then defined and set in the ILS by the ILS technician at the glide path itself. But we can then, obviously, it's important to know what we are measuring. So we can define what kind of alarm conditions for the course align mode, or the course width alarm, or the clearance width alarm. We can also change transmitter. So we need obviously to measure the 2 transmitters, and we need to know which what was measured by the system. Then we can select different number of measurement. We can repeat the same measurement several times, or select, as Luc has shown in his presentation. We can make different alarm condition during the same flight. So going up under certain alarm conditions, then going down using another set of conditions. And then what the software is doing is we have defined, this is obviously user configurable, we have defined some delay for the alarm changes and for the TX changes. So it means that when the drone will climb after the first measurement, the drone will wait 60 or 30 seconds, depending on the change which are required, such as the operator behind the ground station can then call or contact the ILS technicians to give him the instruction to change the alarm conditions. And then the drone can continue and measure the second part of the or continue and make the second measurement. Something which is very important is the takeoff position. So you can manually select or define a position, but typically again we select a position from the database. So it means that we will always, in that case, we put the drone on the exact takeoff position. It is important because in our system, the height or the altitude, the flight altitude are calculated above takeoff location. So we will give the instruction to the drone to fly 20 meters above its takeoff location. So all the calculation of the waypoints are then using also the elevation of the drone from the takeoff location. We can then set a different landing position. For instance, if we do arc flight or some longer mini approach, we could define different takeoff and landing position. Then we can generate the flight plan. So then the flight plan is composed of coordinates, actions. So from takeoff to landing. So it means that the drone can completely autonomously fly. So the pilot just need to trigger the takeoff sequence, and then the automatic takeoff will start, and the drone will then follow the different waypoints. Then the start and stop measurement are defined, so automatically defined. So those start and stop are really the one for the recording of the receiver. So the receiver will start recording from this waypoint to this waypoint, and the second part of the measurement from the waypoint 7 to the point 8, for instance, in that example. Important feature is that we have the geofence automatically calculated. So for any kind of flight, we will define a fence around the flight path, such as the drone cannot fly out of this area. We think that it is definitely even more important when flying at airport, that we are sure that the drone cannot go anywhere else than what is planned. And then when this is finalized, when the operator has checked all the height and that everything is fine, he can upload the flight plan. Okay, so the upload of the flight plan then needs to have the drone connection. So that's is the end of the first part, and let me now start with the video, where you will see a video that we have recorded actually 2 or 3 days ago. The first part, when we connect, is we download the parameters from the drone. So some parameters are necessary to make some calculation within the software. And as soon as we connect, we start seeing live information from the receiver. So if you see that there is some, actually we receive a lot of measurement point, and then for the display of this live measurement information, we only make an average of every 10 measurement. That's why it looks like coming step by step. Then we configure the RTK setup. Then we assign to the base, and then after a few seconds, so it means that we really give this coordinate to the base station, and then the base stations start streaming RTCM correction. And then the drone receives this RTCM connection from the link, and we have this RTK fixed mode. So meaning that now we are at the centimeter level accuracy. So we can then start the configuration of our flight plan. So as I've shown, glide paths, vertical. We select we can also have some side view or some top view of the flight, so that we can check what we are programming. The selection of the alarm conditions. And okay, I select 2, add to mission. Then the selection, here you see there is a small difference. I don't know if you noticed, there was from drone, because I'm connected to the drone. So it's also possible that as soon as I have RTK correction, it is also possible to create a new takeoff point. So we don't need to always have the point from the database. As soon as I have RTK correction on, then my drone position will be accurately calculated. And also using the offset of the GPS antenna, we can make all the calculations in order to use this new point. Then the fence, the mission, and then we upload the flight plan. We have also some other features available in this important confirmation. So we have a lot of warning in the preparation of the mission. The idea behind those warnings is that to make always aware the pilot or the operator about the distance between the drone position and the programming or the programmed drone takeoff position. Also between the takeoff position and the first waypoint. So to be sure that there is no mistake. For instance, you are located at the runway 21 and you want to to measure and you use the runway 3 as a parameter for the drone. So that would be quite not very nice to see the drone flying all above the airport. Then when it is ready, we have to wait for the ATC clearance. So from the tower, for instance, when we have some nice airplane just landing, and then the drone can start and we can start the mission. I have a second video which just will start just after that. So in that case, the pilot like to take off manually and then to start the mission after the takeoff. Here you can see in the background this RTK base station, which is positioned. And this is then exactly what we see during the flight. So behind the ground station, the operator, in that case was me, monitoring the full flight. So monitoring the telemetry information. So we have a lot of different information for the telemetry. We have the batteries, we have the parachute, and we have also the receiver information. So here we see already that the recording has started. So you can see on this part, I don't know if you see, I guess you see my mouse, we have the halt above home, and the drone is climbing. So the drone is measuring, I don't remember exactly what was the values, but like in a range of 100 meters. And then we have the status of the receiver. We have here the information of the time to the next waypoint. This is a little bit fluctuating due to the variation of the speed. And this is very useful also for the operator to start calling the technician to tell him to be ready to change the conditions at the glide path or localizer. Then there's a countdown. So in that case, we have only by default 5 seconds waiting time on top. So the measurement, the first one has finished, and then now we start to record the second 5. During all flight, the technician or the operator can monitor the live information, as well as all important telemetry value. We have, for instance, information in green RTK fixed. So if there is any loss of RTK during the flight, the operator can have this information. We see also satellite information, the HDOP. We have the information of the batteries. So this is only okay, this is all the telemetry information, but obviously there are some additional safety features which are implemented in the autopilot itself, such as the typical battery fail-safe. So if the batteries goes below a certain level voltage, then the drone will automatically trigger a return to launch operation. Then we have here all the information coming from the autopilot. Most of the time during the flight, there is no additional information than the one before takeoff. Also, so here the drone is still 26 meters above ground. So we are reaching actually the end of the second file, and now the drone the receiver initiate the VLAN. So he has another connection, which is with a wireless LAN. So he start his access point, and we start downloading. While the drone is still flying, we start downloading already the result. And the drone even did not land, that the SDR processing of the first measurement is already under progress. So we see here information that we are doing SDR1 process. The drone is on the ground, has landed, is disarmed. We can see here the status. Important also is that we have integrated, if you see on the left part, while the process is still going, we have integrating in the left part some in-flight commands. So where we can turn on or off the lights. This is the first point. But also some, again, safety features such as so it is possible to trigger some special flight mode like return to launch and landing action from the ground station. So in case of pilot and okay, I won't try to say the word. If the pilot is not able anymore to control the drone, then the operator can still trigger some special action, even trigger the parachute deployment in the worst case. Here we are so now downloading processing the second measurement. So after a few minutes, or even less than 1 minute after landing, we have the two results available. Obviously, the processing depends on where you are flying and how long the flight is. So the further we are flying, typically more information we have in the file, and the bigger is the file, also the speed. So yeah, this is the end of this second video, and I will now go back to the software to now display the results. So now that the drone has flown, the drone has the receiver has measured, we have downloaded and processed the result. We can now see the different result that has been realized. So we have the list of different measurements which has been done. We have the filter that can be applied, and then we can select different colors for the result, and then display our measurement. Then we have some features. So you have then we display the DDM curves, the SDM, the RF level. We can also display the RTK fixed status. So in case of any strange result, you can check that the RTK was still on, because that could be a problem during the flight. We have also the horizontal and vertical accuracy. So in that case, we are really between 2 and 3 centimeters. We have the so-called coupled cursor. So when I click on the DDM value, then I see the corresponding SDM and the corresponding RF level value. We can obviously enlarge this result. We can also, here on that part, we have different values which are calculated. We can overlay different results. We can also select different scales, and we can then also generate the report. Okay, I've already the report. Okay, it did not open automatically. Here is my report. So I have generated then my report, where I will basically find again all the same information, but in the report, there is a space available for your logo. You find the measurement that has been carried out, then the table with all the values calculated, and then different display of result, DDM width vector, and so on. This part obviously can be also tailored to your specific needs. This is the typical report which are required by German DFS currently. Okay, so I think it's now time for me to give the floor again to Luc to conclude this webinar. Thank you very much.
Thank you very much, Cédric. I think this was very interesting, hopefully for everybody to get a good impression on how we deal with the NavAidDrone software and with the whole setup when we are on field. I will not do the short conclusion, because we have only one remaining question at the moment. I would suggest that we can even just answer this question now, and then I would conclude the web seminar. So, Cédric, maybe you can answer. I don't know if you see the question.
Yes, okay, so I see the question. So GNSS 1 and 2, so actually our drone has two GPS. The first one is a normal GPS, so without RTK correction, and has also a compass. The second one, the RTK, has no compass inside. For compasses, maybe I go a little bit further. For compasses, we have two additional internal compasses in the autopilot. So the drone is using for flying and for measuring, but this is also user configurable. Is using the RTK or the base GPS, which is in that case the RTK1. So as well for coordinates or for long glide positioning, as well as for height positioning. Then if we lose GPS, okay, that we have to be honest, that never happened. I mean, we never have lost any GPS signal or even both of them together. But that's why also we have 2 GPS in case of any issue. Worst case, the drone will stay at this location and switch back to the hold mode. So meaning that it will fall back to the barometer as a source of altitude and keep the altitude waiting for the pilot to take over. Because obviously, if there is no more GPS information, the drone cannot fly back home. So the pilot has somehow to manually recover the control or take the control of the drone and bring it back. And yeah, that could happen only in case of very strong interferences. And in that case, we could expect that the drone moving out from a special area would recover GPS signal.
Okay, thank you, Cedric, for the answer to this interesting question. Because we were just talking about safety, maybe a last slide also from my side, when we are talking about safe operation in an airport environment, of course, we have also to talk about integration in UTM systems. UTM systems are currently developed in different parts of this world. We have, for example, for Germany, already created an interface to the solution provided by the company Dronic. And here on this slide, you see an example of our drone here, which can be traced by a special software. Actually, it's a web-based application together with other information. For example, here, this was an example when we made a NavAidDrone mission together or in parallel to a flight inspection. It was also a very, very interesting project. All right, so we are touching the 1 hour time limit. Let me just give you a short outlook. We don't have time to go too much into the details, but that I said at the beginning, we want the NavAidDrone to be implemented in the airport, also for other applications. One application is to check VUR, especially the DVUR installation, where, for example, it's quite critical to find the bearing errors on the sideband antennas. This is something that can be done with the VUR. Then the drone can also be used for inspection of PAPI, precision approach path indicator. Here, our concept is actually to use the same drone, because this is the drone that you have already registered, that your people are used to operate in the airport, and to just exchange the payload. Instead of the payload with the ILS measurement receiver, we install a payload with a high-end camera system and another software on it. I mean, the camera software, not the drone software, and we can then perform PAPI. And our concept is especially to be able to do the PAPI inspection, for example, at the middle marker. This is the point where we consider it's very useful to perform the glide path measurement. And because you are anywhere there, you have already the clearance to fly there from the tower, then you can also do the PAPI inspection from there. You can do it from other places, of course, but this is one possibility. And last but not least, we are currently also working together with FCS and with Jochen Bredemeyer on a radar application. This will be called the NavAidDrone. Here, the target is to have a complete new solution to measure ATC surveillance and air defense radars. And I think this is a topic for itself, and we will for sure organize another presentation on this specific topic as soon as possible. All right, so thank you very much for your attention to this web seminar. As a short conclusion, the title of our event was "What are the benefits of the NavAidDrone?" And actually, we have tried and to give you some explanation about the different aspects that we consider to be absolutely important when using drone for NavAid inspection. We were talking about integrity and accuracy of the measurement. We were talking about safe operation in airport environment, in the efficiency in operational procedures, and we are really very happy that this afternoon the software presentation went well. All in all, the target, of course, for you as users are financial savings. financial savings because you can use the NavAidDrone to do much better and much efficient ground measurement. Ground measurement, and you can use the NavAidDrone to reduce the flight inspection effort in a certain way, and especially also with the long-term topic of extension of flight inspection intervals. We have seen that we want to leverage the use of the NavAidDrone for other application. And last but not least, we can also say that if we, especially compared to flight inspection aircraft, with the NavAidDrone, we provide a contribution to the global evolution towards green technology. That's not the conclusion of our web seminar. We thank you very much, all of you, for your attention. As we said at the beginning, there will be a replay of the web seminar. You will get the link until end of the week. And we look forward to stay in contact with you for further question and further discussion on this very well innovation. Thank you very much. Bye-bye.